everyone, and thanks for joining today's webinar. The subject, what we're going to be talking about today is how to program and use diagnostics on the 905U series of radios. And just a quick introduction, my name's Brian Cunningham. I'm with ELPRO Technologies, and I've been with the company for, let's see, over 10 years now. So I know these radios pretty thoroughly, and I've been in the wireless business for just over 20 years now as well. Okay, so let's get started. Okay, first thing is I just wanted to have a quick introduction to the ELPRO product line and to show you which products we're going to be talking about today. These are all the products that ELPRO manufactures. The top row are radio systems that have I/O built into the radio. So these radios have 4 to 20 milliamp inputs and outputs, discrete inputs and outputs, etc. In the second row, these are our gateway type products, typically located in the control room. They can communicate using protocols to PLCs or DCS or a computer running a SCADA software program. On the third row, these are our Ethernet pass-through modems. So whatever you put into one radio comes out the opposite radio. And then we have cellular devices, or sorry, serial devices that do the same, and a cellular modem as well. Now today we're going to run through a live demonstration using the 905UG ET1 Ethernet gateway, and the opposite radio is going to be the 905U-1. Okay, here's some quick specs on the 905U-1. It's a 900 megahertz frequency hopper. Long distance radio, maximum range is 20 miles. That's the absolute max if you elevate the antennas at least about 100 feet above ground, and you use high gain antennas and you have clear line of sight from one end to the other. This radio can be expanded. It has a variety of inputs that you can see right here. Just in a nutshell, the 905U-1 has all the capabilities listed in this column right here. And to quickly summarize, it's got 2 analog inputs, 2 analog outputs. It's got 4 digital inputs and then 4 relay outputs, all built into this device right here. Now we also build a 905U-2, -3, -4. These radios have been obsoleted. However, we did build thousands of these radios, so you may encounter them on occasion out in the field. If the I/O on board is not enough, there is a RS-45 terminal block just down here, and that allows you to connect it to our 115S serial expansion modules. Radio transmissions are triggered using a change of state. So if any of the discrete inputs across the bottom change state, then the radio will immediately transmit that down. And if any of the analog values change by more than 0.5 milliamp, it will also trigger a transmission. As well, we have routine updates in case none of those inputs change at all. The radio also has a built-in battery charging circuit. So if we apply 24 volts across the bottom, and we hook a 12-volt battery to these 2 terminals up here, when the 24 volts is present, it'll put a trickle charge onto the battery. And if the 24 volt power is lost, the battery then takes over and powers the radio, providing seamless operation. In addition, there is a built-in solar charge regulator or a solar panel of up to 30 watts. So this means you don't need to have a separate item as a solar charge regulator. You hook the solar panel up right here, you hook your battery up right here, and presto, the unit will operate continuously. Now, one thing I do want to mention is in this demo, I'm going to be pressing a red button down to put the radio into diagnostics mode. The red button is located underneath this blue plastic cover. So if you pop off this cover with a flathead screwdriver, you'll see a large red button right in the middle, and that is the button that I will be pressing to put the radio into diagnostics mode. Okay, next one is the opposite radio is our 905 UG, and it's the ET1 variant of our 905 UG series. Now, we have several different models of 905 UG. This is the most popular one that we sell and that we deal with today. This shows you all of the protocols. It can do Modbus RTU master, Modbus RTU slave. It can do Modbus TCP, so an Ethernet protocol, Modbus TCP server. It can also do Allen Bradley's Ethernet IP protocol and Allen Bradley's older serial DF1 protocol. Now, this radio can communicate with the 905U-1234 series of radios. It can also communicate with the 905UK and the 905U-L-TMR radios. So all of these radios, all those models there, plus this guy here, they can all communicate with each other. The radio has 10,000 registers on board for data storage. And so typically this radio is going to be in a control room, although occasionally it'll be at a remote site interfacing with a PLC and taking that information from a PLC and then radioing that back to your control room where it's being read using Modbus or Ethernet IP or whatnot. Now the radio inside is the same as the other models. It's a 1 watt, 900 megahertz frequency hopping spread spectrum radio. And as well, I should mention, the radio has 8 DIO across the bottom. So they can be digital inputs or digital outputs. And you can see there are LEDs next to each one. So if I turn on the one of these digital inputs, I'll see that LED turn on as well. So it's very simple to see whether an input is active or inactive just by looking at the LEDs. As well, there is an RS-45 terminal block on the top of the radio here, and it can connect to our 115S series of serial expander modules, and you can increase the I/O count. So we've got modules that have 8 analog inputs plus 8 digital DIO. And then we have a unit that's got analog outputs, and then we have a unit that just has strictly digital I/O. And you can hook up to 10 of those to a single gateway, so you can have literally dozens and dozens of I/O points off the radio if you so desire. Most of the time, however, it is communicating using a protocol. So what we would typical setup, we would have dozens of these remote radios in the field. They're all sending their data back to this gateway, which is acting as the master, and this gateway is communicating to a DCS system. Okay, inside of the 905 UG, this is what the structure of the radio looks like. So you've got the actual radio circuit board, obviously connected to the antenna, and then we have this radio interface and the I/O database, which is connected to the onboard I/O, the 8 discrete signals that we just mentioned there. Then we have a separate circuit board that does the field bus interface. And this field bus interface for the ET1 variant of the 905 UG, as I mentioned, is Modbus TCP or Allen Bradley's Ethernet IP protocol. And so one of the steps that we have to do is we have to map the data. We have to transfer it from the radio interface database to the field bus interface database before it can be read using Modbus or Ethernet IP. So that's an additional step. So this is a separate circuit board laid on top of the radio database circuit board. And so therefore there is a second step. Once we transfer the data over the air from a remote radio in through the antenna port into this radio database, if we wish to use that as Modbus or Ethernet IP, we have to transfer it over, and that's a second step. Okay, I'm going to show you all that in just a minute. Okay, here's what we have for today's test setup. And this is the last of the PowerPoint part. I'm going to run the software and we'll go ahead and show you how that works in just a minute here. But here's what we're going to do. We're going to take digital input 1 from this guy here, and we're going to send it to digital output 1 on this radio. Now on the gateway radio, all the registers are identified by a number, and digital output 1 is register 4320. Then what we're going to do is we're going to create a mapping sending digital input 4 from this gateway radio back to the 905U-1 to digital output 1 on the 905U-1. Okay, so this is the register map. The 8 DIO can act as inputs or outputs, but obviously only one at a time. So in this case, if you wanted DIO1 to act as an input, address it using register 4300. If you wanted to use that DIO1 as an output, you would address it as register 4320. And keeping in mind, you can't do both at the same time. It can only be an input or an output, not both at the same time. Okay, so I think that's pretty much, oh, there we go. Oh, just a quick setup here, a quick mention. The wiring for the power on these two radios here. For the 905UG, we connect our 24-volt power source between SUP1 and ground, and we're good to go. If we wanted to connect a battery, then we would connect it between the BAT and ground. And it's designed for a typical sealed lead acid 12-volt battery. And as I mentioned, if this power gets lost, the radio runs off battery power. For the 905U-1, very similar. This for your 24-volt DC power supply, we connect it between SUP1 or supply 1 and ground. And then the battery would, of course, be connected to these two terminals over here. Now, this power supply has to be 15 to 30 volts. If the power supply is less than 15 to 30 volts, then we connect it to these two terminals right here. So this could either be a standard battery, or it could be a 12-volt power source, like just a 12-volt power supply. The input range is 10 to 15 volts on these two terminals here. Okay, so I have these two radios wired up right here, and that's the last part. I'm just going to head back to our test setup here, just so that we can refresh our memory as to what registers we're going to use. And now I'm going to run our software. Okay, so we'll just head back over here, and I'm going to run the E-Series configuration software. Okay, so the E-Series, this is what we use to communicate with all the 905U series of radios. And on our website, just go ahead and download the latest. You can see we've got version 2.3, build 434 is our latest. Okay, so now what I want to do is I want to open a new project. And what it's going to want to do is to create a new directory. So I'm going to just call this example. Oops, we'll just call it training. Okay. And I'll hit OK. And what it's going to do is it's going to ask you if you want to create a new directory, which is highly recommended. The configuration files consist of about 15 or 16 different files. And so therefore, it's much simpler if you keep all those files in a single directory. And at a later date, if you wish to create a backup copy, we have an option of zipping those 15 or 16 files. So you can email them to a customer or store them as a single zip file. Okay, so here's the start menu here. This is the name of the project that we just created here. And this is the random system address, which is a randomly generated number between 0 and 32,000. and the system address has to be the same on all radios in order for them to communicate. But one interesting thing to be aware of is that the even system address numbers, use the upper half of the 900 megahertz band, and the odd system addresses use the lower half of the 900 megahertz band. So we divide the 900 megahertz band into 902 to 916, and that's the lower half, and then the upper half operates from 916 to 928. So just keep that in mind if you have multiple ELPRO networks in the same area. Okay. So then what we do is we click on units, and then we need to tell the software what models of radios we will be dealing with. The first radio I have is the 905U-1. Note that for some reason they have dropped the U in the model numbers, so just select 905-1. Okay. Now it's asking if I want to manually select the unit address. Each radio has to have a unique unit address. I will just select no, and I'm going to let the software automatically assign the address. Now when I click up here under units, I can see my first radio has been added. Next, I'm going to add the gateway radio. So we go ahead and select the 905-G radio. And then it asks us which version of that radio do we have, because we do have several different models. I have the Ethernet version here in front of me. The ET1 is the Ethernet version. Okay. Again, it's asking me if I want to select the address. So I'm going to select no. So now I've got my two radios in my project tree. And if you have more radios, just keep on adding them all in. Now, when I click on the title of each radio, this is where we would do things like programming each unit or loading a unit. And loading unit pulls the configuration from the radio into the software. Programming unit downloads the configuration from the software into the radio. And you can see this is the unit address, and each radio must have a unique unit address in the network. And you can see the same for the 905UG. The software just starts at 1 and makes the unit addresses, increments the unit addresses up in that fashion. Now, if you click over here on the plus sign, we can expand the tree here so that we can now see all of the different options available for these radios. So the number one thing you'll have to do on pretty much all radios is create mappings. And mappings are done from the sending radio. So in this case, I want to send digital input 1 to digital DIO1 on the opposite radio. So I click New IO Mapping. And I start by selecting the input on the sending radio here. Then I work my way across the screen. I select the destination radio. And then we have to tell it what address or what register we want to store on the opposite radio. In this case, I know that register 4320 is digital DIO1. Okay, so I select the proper register and we hit apply. Okay. Then the next thing we have to do is we want to create the mapping on the 905UG to send the that DIO4 back to DO1 on the 905U1. Now, as soon as I click away from the radio, the software tells me that both the sending and the receiving radio have to be programmed in order for this new mapping to take effect. Okay. So just as a quick note or a quick reminder, the sending and the receiving ends of each radio need to be programmed for new mapping. Not any repeaters in between, just the sending and receiving radios. Okay, so now I'm in the mappings menu of my gateway radio. I click a new IO mapping, and I start by telling it what register on the gateway radio do I want to send over. And remember, it was register 4303 is DIO4. Whoops, it's 4303. There we go. is DIO4. Then I select the destination radio, and it tells me it's got all these outputs available, and I want to send it to digital output 1 on the destination radio. Okay, I hit apply, and let's just double check that mapping here. Yep, I just wanted to make sure that we had acknowledged message ticked. Okay, so acknowledged message means that the 905U1 is going to send an ACK back to the 905UG when it receives the message. Okay, so we can hit apply, and now we are pretty much good to go. Now I'm going to give you a super quick rundown on the rest of these parameters so you can understand them a little later on. And then we're going to power up these radios, run into the diagnostics, and I'll show you how that works as well. So we have our update times here. And this is assuming that an input does not change state. How often will it transmit? And our default is just every 10 minutes. But if you're doing a site survey or bench testing it, you're going to want to set it to something much faster. So in this case, I'm going to set it to the fastest it'll go, which is every 7 seconds. Okay, so we hit OK, and that's set for 7 seconds. Then we have a parameter called output reset. And this is what happens if the radio loses communications. So for example, I've got this mapping is going to digital output 1. If communications fail or this radio loses power, what do you want to happen to digital output 1? And your options are either it can freeze at its last known value, which is what will occur with this default setting, or I click disable and I enter in a value that has to be longer than the update time of the sending radio. Okay. Sensitivities, this is when a transmission is triggered. 3% of 20 milliamps is approximately half a milliamp. So I could set this to a little bit tighter, a little bit looser as needed, and that would make the radio transmit more frequently or less frequently. We've got some pulse input settings, pulse output settings. We have a set point setting where we can have analog input 1 sent to a digital output to simulate filling a tank. Then we have our debounce settings, and this is for contact debounce. So in other words, this radio is going to wait a half a second before it registers that as a change. So there will be a half-second delay for contact debounce. Same with the analog. If we get a little spike that goes all the way up to 20 milliamps, but then back down to a normal value, and that spike only lasts for 1/10 of a second, well, that's just noise. We don't want the radio transmitting noise. So there's another half-second delay on the analog. On the analog inputs. Then we have serial units, which we could add to this radio in this menu here. And let's see, so in the 905UG gateway, you'll see a couple of different options here. We've got the mappings. Then we have block mappings. This is where we can send a block of registers from one gateway to another. Then we have our field bus configuration. And this is for transferring the data from the radio database to the field bus database. And it's very similar to the other types of mappings. You just click on new field bus mapping and you to and from and that sort of thing. So, reasonably straightforward there. Sensitivities. This just determines when a radio triggers a transmission. If we convert 0 to 20 milliamps into byte counts, the scale is 32,767. So a sensitivity of 1,000 byte counts also equates to approximately half a milliamp. So that's the default, but we could change it and measure sensitivity blocks if we needed to. It would cause the radio to either transmit more frequently or less frequently, depending on how much a input variable changes. Okay, then we have our Ethernet settings, and this is where we set the IP address of the radio, set it to whatever you like. If we're using Modbus, we have to make sure we've got this ticked, or if we're using Allen Bradley's Ethernet IP, we have to make sure this one is ticked over here. Okay. Then we have the update times. This is just how often this is going to transmit here. Now I'm going to set this to as fast as it'll go because we don't want to wait for potentially 10 minutes, or I don't want to have to fiddle with jumpers, inserting and removing to cause the radio to transmit. So I'm going to set it to transmit every 10 seconds, which is as fast as it'll go. Okay, then we have our COM fail times. Just as I was describing out here, COM fail is the same thing as output reset. What do you want to happen to this register if communications are lost? Options are either flatline, hold the last known value, or turn the output off. Then we have some unit details up here. Number of transmission retries. So this radio, if it does not get an acknowledgement from the opposite, it's going to try it 4 more times. And if it's sending to a one-way device that is a receive-only device, then it's going to send the message 3 times because a one-way device cannot send back an acknowledgement. And then lastly, we have our serial units. These are currently disabled because we have this radio set to Ethernet protocol. Oh, I guess we could enable it right here. Yeah, if we enable it down here. There we go, that's it. Yeah, so we can have the protocol working at the same time as we have serial units connected to the RS-485 port on the radio. Okay, so now time for the live demo part. The first thing I'm going to do is I have a USB to serial converter cable plugged into my laptop. I'm going to head to the serial port, and I'm going to make sure that there's a tick mark next to COM3, which is what the USB driver, the COM port number assigned to the USB driver. Okay, so I have to have a tick mark here, and then you can verify that right down here by looking at COM port 3 selected. Okay, let's see. So now we've got that, I'm going to go ahead and plug in power to the radios. Okay. The radios take about half a second to boot up, so they boot up pretty much instantaneously. And then I'm going to make sure my serial cable is plugged into my 905U-1, and I'm going to click on Program Unit. Okay. And now what it's telling me is that this radio has a system address that is different from the system address in the database, which is perfectly normal. And it's just telling me, yeah, if you want to program it, the system address inside the radio will be changed to reflect the system address of this project, which is something I want to occur. Okay, and it's finished programming, and it's telling me that I have to power cycle this unit to complete the program. Okay, so I'll acknowledge that message, head over to my power switch. Remove power for just 2 or 3 seconds is fine. You don't have to pull power for for 10 seconds or anything like that. Just 2 or 3 seconds is fine. Okay. Then I'm going to click on my gateway radio, and I'm going to click Program Unit. But before I do that, I have to pull the serial cable out of the 905U-1, stick it into the serial port of the 905U-G. And the second thing I have to do is I have to press this recessed button on the 905UG for 5 seconds or longer to enable it to be programmed. So the recessed button is near the antenna port, and you will need a small slotted screwdriver. Okay, so I'm pressing that button down, and there we go. After 5 seconds, the ACT LED will begin flashing rapidly, and the radio can now be programmed. Okay. Okay, so we're setting all this up. And there we go. Now with the gateways, the software can reset the module, so I don't have to cycle power. I can just click yes, and it tells me the unit has been power cycled or reset. Okay. Now these radios should be transmitting between each other. If I look at the TX and RX LEDs on the radio, I can see there is activity there. And what I have is I have two small whip antennas. So these antennas are about 5 inches tall, and I have attenuators in series with both antennas. And that's because these two radios are just side by side. So otherwise, we would have there would be some issues. They would essentially be saturating if we didn't have attenuators connected, and we may lose radio communications between them. So now what I'm going to do is I'm going to click on my one radio here, and I'm going to show you how to set up the diagnostics. Now, what I can do is I can trigger inputs and I can look at the LEDs to make sure they're working. But I really want to spend some time on the diagnostics and show you how that is set up and how to read the radio signal strength of any given radio. So what I do is I start my diagnostics menu, and then I click on terminal. Now I have to put the radio into diagnostics mode. And remember that red button I told you about underneath the blue plastic cover? I popped the cover off. I'm now holding that button down for 5 seconds. After 5 seconds, the RX LED on the radio will go solid orange, and you'll see this menu up here. And I'm going to select C. So I'm typing in the letter C for communications. And now what I do is I click Stop Terminal, Start Comms, and the software wants to make sure I've got it in Monitor Comms mode, which I do. And here we go. Now we can see some traffic going back and forth between the two radios. Okay, now some interesting things. We have our timestamps over here. This is always very useful to have the timestamps enabled. And you can see we've got a bunch of TXs, we've got some RXs, we've got TXs, and that tells you the direction of traffic. Okay? And I set my radios to transmit every 7 seconds on one radio and 10 seconds on the gateway. So we should see a fair bit of traffic build up fairly quickly. Okay. Now what I'm going to do is I'm going to stop communications, and I'm going to explain what we're seeing on the screen, because if I don't stop communications, what happens is this screen will just continuously scroll down. Okay. So I'm going to head up here, and I'll just pick any particular line. Well, let's see. I'll start with a transmit line here. Okay. So we can see this is a transmit line, and what I want to do is just explain what these numbers in hex mean. The first 4 digits are the system address of the radio, and if you just click on any line, it'll convert that system address from hex into decimal, so that we can understand what it is. Okay. The next 4 digits, the 8 is just a prefix that you can see is common here to everything, whether it's transmitting or receiving. But the 2 is the address of the destination radio. So that's saying that this message was destined for remote radio number 2, which is our 905UG. And let's see, this message, the purpose of this message was an acknowledgement of the previous transmission. Okay. Then the last 2 digits here, these are going to be the last 4 digits are the CRC. Okay. So then, oh, I forgot to mention, so we see the 82, the 2 is the destination radio. We see the 81, 1 indicates the unit address of the source radio, and then the 00 is just a data spacer. Okay. Then if we go to the next line, this next line is a transmit line. It shows a command type message going from radio number 1 to remote radio number 2. So that's going from the 905U1 to the 905UG. Okay. And the message is IO register 4320 equals off. Okay. Now, by clicking on these different boxes here, we could change the meaning of it. Now, specifically, this message is a digital message. So by clicking digital would be more appropriate. It gives you a better method of display. But if it were an analog value, I would have to click here, and that would tell me what the 16-bit hex value equates to. Okay, so I'm going to leave it with the digital value there. Okay, so that was the command going out to the gateway radio. The next line is an acknowledgement from this gateway coming back to the 905U1. And because it was a received message, this is showing me what the RSSI is. Okay? The RSSI for these radios generally pegs out at the maximum value is -30. And the only reason I'm not seeing that is because I have attenuators in series with the antenna. Now, for every RX line that you'll see here, there's always a negative number. And that is what is showing what the RSSI is. Okay? Now, with these two radios side by side, I would expect the RSSI to be very strong. I would not expect to see a value of -94. The threshold of reception for these radios is about -110. At a value of -100, we begin to see a number of errors. At a value of -105, we'll see at least 50% of those values being errored. And at 110, we're very lucky, -110 dBm, we'd be very lucky to see any of the values come in accurately. Now, why we are seeing -94 is because of clutter in my office environment. Because there are all kinds of equipment, I've got all kinds of radios, particularly metal surfaces reflect radio waves quite a bit. And the reason we don't see this consistently is because it's a frequency hopper and it's changing frequency. So when I see -94, what that means is that one radio wave took off in one direction and another radio wave took off in the opposite direction and bounced off something in my office. And both the radio waves arrived at the 905U1's antenna significantly out of phase of one another. Now, if these radio waves were exactly 180 degrees out of phase of one another, we would see no reception at all. But they are not quite 100% out of phase, and that's why we're seeing this very weak signal. So what do? We just ignore that value. This is what the RSSI actually is. It's roughly -38, roughly -40. This type of condition is perfectly normal. So keep in mind that here we've seen pretty consistent communications. For each transmit, an acknowledgement comes back. The transmit goes out, an acknowledgement comes back. If radio communications fail, then we would see a bunch of transmits all in a row of the same message. So like in this case right here, looks like we transmitted a message out once, never got the acknowledgement back, so maybe 200 milliseconds, we sent the same message out again. And then finally, we got the acknowledgement back from the opposite radio. Perfectly normal radio operation. All radios are designed for this type of thing. All radios do retries automatically exactly because of this type of communication. So for a radio system to be doing retries, perfectly normal to be doing 1 or 2 retries. But if it has to do all 5 retries, if you see the same line 5 times in a row, that means the message never got an acknowledgement from the remote site. Okay, so let's see. So we've talked about the RSSI values here, and you can click on any line, and it'll show you, what the RSSI is, same as the number that you'll see up here. And as we go through each line, it shows you what type of message was sent back and forth. Okay, so here we go. It's another one. Register 4320 is commanded to be off on the gateway radio here. And the next message is the gateway sending an acknowledgement back that, yes, I got that message. Then the next message is coming from the gateway, it's telling digital output 1 to turn off. Okay, and we can see we got a nice strong RSSI. And then the next message is radio number 1 acknowledging that message, sending an ACK back to the gateway, telling the gateway that yes, I got that message. Okay. Now, sometimes you're going to see a whole ton of different unit addresses all over the place because you might have a large network with, 20 or 30 or 50 radios or something like that. And this is how you can kind of figure out who was communicating with who. And oftentimes what you'll see is you'll be plugged into radio number 1, but you'll see messages going back and forth between radios 5 and 6. Well, those messages are not destined for radio 1. But 5 and 6 have some messages they need to send back and forth between each other, and radio number 1 can hear them. So that would be a communication that is not really of importance to us at radio number 1. Normally what we do is we would create this communications log at the problem radio location. Okay, that's pretty much it for today's demo here. I just wanted to show you how to set up the comms log. Now, what's often a very good idea is if you're doing a site survey, is log this value to a file, and it'll create a text file, and then save that text file as the name of the location that you're at. And then you'll be able to see what the communications were like at that particular remote site. Now, communications, the RSSI value may jump around a fair bit. However, if you have clear line of sight and you have your RSSI between our desired values of -30 and -90, if you have clear line of sight, the RSSI should be very, very consistent. We wouldn't expect to see something like this very often at all. So clear line of sight, the RSSI is very consistent, may jump around by 3 or 4 dB. But if we have trees or houses in the way, then the trees are going to cause a scattering effect, and the radio values will jump around quite a bit. So let's say we had a couple of trees in the path, and the radios were, say, 1 mile apart. And let's say we had 3 or 4 trees blocking line of sight, then we would expect to see an RSSI of, say, between -70 and -80. So it'll bounce around a fair bit, but we could say the RSSI, averaging things out, would probably be around -75. If we had clear line of sight over 1 mile, no trees in the path, we would expect the RSSI probably to be about -70, rock steady. So it might bounce around -68, -71, but it's going to be within 2 or 3 dB consistently. There might be the odd case where we get a multipath condition to occur, but it's far less common when there is clear line of sight between 2 locations.